Hey folks, Mr. Wemp here again. Last time we talked about just the basics of mechanical advantage. This time we're going to talk about specifically levers. So with a lever, we have a few different kinds of levers. And a lever is a very simple object. We have, let's do nice pretty ones here. We have, let's see, 1, 2, 3 types of levers. Okay, so I'm going to mark that down that there are 3 types, and those 3 types are first, second, and third class. Okay, now this doesn't have anything to do with the quality that they are. There's just the 3 types: first class lever, second class lever, and third class lever. Okay, and if I take each one of these levers and I put a force on them, or a weight to be lifted. Okay, so those are newtons there. So each one of these 3 levers has a newton. So a first class lever, this is first class, is a very basic lever. It's what we all know, like a teeter-totter, where you have your force here, you have your effort force here, and you have your fulcrum. The fulcrum is the piece in the middle. Okay, so they're very balanced. It's nice and easy. Okay, a second class lever basically has the fulcrum over here on the end, okay, and the resistance, oops, I have it in the wrong spot. The resistance is not over here. The resistance is actually right here, and our effort is here. So here's our effort, there's our resistance. Over here we had a resistance and an effort. Now remember, we use effort and resistance in our mechanical advantage calculations. So that's a second class lever. Now what does that look like? You pick up here, picking up a weight here, and it pivots right here. What kind of object would that be? Is it similar to a wheelbarrow? You have your bucket here, you pick it up, there's your wheel, you pick it up like that. So we have a teeter-totter, a wheelbarrow, and then finally we have a third class lever. And a third class lever is kind of different in that the fulcrum again is at the end. Okay, our force is over here, so this is our resistance, and then to pick this thing up we're actually going to apply a force here, and that is our effort. So our effort is closer to the fulcrum than our resistance is. So this has a mechanical advantage greater than 1, this has a mechanical advantage greater than 1, this guy has a mechanical advantage less than 1. So this might be more like a shovel. So if your hand is here, your other hand's here, and you're picking the weight up there, it works. It's ideal to have a higher mechanical advantage, but that's okay. So there's our 3 types of levers. Okay, to calculate those, we are going to let's see, I need to add a page here. Just move that to there. Oh, it's not working. Okay, we'll just leave it like this for now. To calculate these, we use our distances. So if we have a lever and a fulcrum and a resistance and a effort, we could calculate this pretty easily. So we're either going to have an ideal mechanical advantage, and we're going to measure our distance of the effort to the fulcrum, and then our distance of the resistance to the fulcrum, and we'll divide, let's see, IMA is equal to distance of the effort over distance of the resistance. That gives us our ideal mechanical advantage. Or we could figure out our AMA, which is the force of the resistance over the force of the effort. Okay, so we can figure out both of those and get an efficiency. But what if we don't have that right there? Okay, so let's pretend for a minute that we don't have this guy right there. Now we've got a problem. I have an effort force. Okay, so I have an effort force. I have a resistance force. Okay, and I have a distance for the resistance. Now I don't have enough information to solve this, but I do know that this is a lever and it's balanced. Okay, so we're going to be in what's called static equilibrium. And if we're in static equilibrium, that means that the whole thing has to be balanced. There's nothing different on both sides. So I'm actually going to go to a new page here. And so let's see, static. Static means not moving. Let's see if I can spell this right. We'll just call it static equilibrium. That'll be fine right there. Okay. So I've got this lever, I've got a fulcrum, I've got a resistance and an effort. Now I know my force of the effort, I know my force of the resistance, I know my distance of the resistance, but I do not know the distance of my effort. Okay, this is equal to big fat question mark. What is that? I don't know. Well, in static equilibrium we have something called a moment. A moment is like torque, so a moment equals a turning or twisting force. So there's a twisting force. So a twisting force looks like that. Okay, so it's turning around an axis. So there's a pivot point. Well, on a lever, do we have a pivot point? We sure do, right there. Okay, so if we've got a pivot point, we know that there's some moments going on over here. So we have a moment force over here and a moment force over here. And if this whole thing is balanced and equal, what can you say about the moment forces? Could you say that the moment force of the effort is equal to the moment force of the resistance? Yes, you could. So what we know there is that our twisting force, so this guy is wanting to go that way, this guy is wanting to go that way, and if the whole thing is balanced, there's no force higher than the other. So the moment of the effort is equal to the moment of the resistance. Okay? Well, okay, that's fine, but how do we find a moment? Well, it turns out that a moment is a twisting force. It's also equal to, guess what? Force times distance. It's a little bit different distance, a perpendicular distance, but for our purposes we have a distance here and we have a force. So that means we can find out what the moments are. So this equation right here would look like what? Well, we have Fe times DE is equal to FR times dr. Okay, that's a moment equation. Moment EQ. All right, so it's a moment EQ. Now, if we have this guy right here and this guy right here equal to each other, that's very simple to solve for that. So if I let's see, I know this one. I don't know this one. Do I know the distance of my resistance? I do, so I know that. Do I know the force of my effort? Yes. So I don't know this right here. I could easily solve for that and find the distance. Okay, this is called using a static equilibrium equation. So this is a static EQ equation. Okay, that's how you find it. Now, later on in the year, we're going to talk more about moments and that force times distance. But for right now, you just need to know force times distance is equal to a moment. You could also say if these are equal, this also equals the sum of the moments is equal to 0. Okay, so remember that too, because this is not moving, so nothing's twisting. Okay, so if we've got that, let's go back to our lever for a minute. Let me drag that up there. So now we're going to do an example problem real quick. So we've got this lever. We've got it with a little piece there. There's our fulcrum. All right. Now let's do, what do you want? Purple. I like purple. So we're going to put a force there and a force there. Okay. Now we know that this guy right here is going to be 15 pounds. So we know that this is a 15-pound force going down. Okay, there's our effort. Oops, excuse me, I wrote resistance, sorry. That is going to be our effort. Alright, we know that the distance here is 5.5 inches from there to there. Okay, so there's our effort force, there's our effort distance. So this is DE, this is FE. Okay, there's some stuff that we don't know though. This is our resistance here, and this is our resistance distance, which we don't know quite yet. All right, so let's see, what can we do? Let's throw in a number. We have well, let's find the moment for this side. So the moment is equal to force times distance, which is equal to 15 pounds times 5.5 inches. Okay, and that gives us a total of 82.5 pound inches. All right, so we know that that's our moment on that side. Now over here, if we put in a resistance force, let's see, do we have that? If we put in a resistance force of 36 2/3 pounds, kind of a weird number, I know. Let's see, it's 36 2/3, so 36.66 pounds. If we have that as our resistance, so this is our resistance force, we can do our moment equation here. So our moment is equal to force times distance, and we have a force of 36.66 times dr is equal, oops, that's not an E, you want a moment, is equal to our moment. All right, now what did I say before about moments? On this thing here we have the effort moment is equal to the resistance moment. So if these are equal to each other, I can say that this equation here, this A2.5, is equal. So this whole section is all equal to each other, right? So if they're all equal, I can say that 82.5 pounds per inch is equal to 36.66 pounds times the distance of my resistance. And then we do some simple algebra there and we can figure that out. So we'll divide this side by 36.66 lb. Whoops, don't want to right click on that. lb. And what we end up doing is crossing that out. And if we divide this by 36.66 lb, we cross out the pounds and we get a number, let's see, 82.5 divided by 36.66, we get 2.25 pounds. So 2.25, whoops, not pounds because we crossed pounds out, inches is equal to the resistance distance. So if this was 5.5 inches, we now have a number here, and we can take that and plug it in right there for 2.25 inches. Okay, so there's how you would figure that guy out right there. Now there's one other thing that you have to do with your levers, and that is to find you can find the actual mechanical advantage or the ideal mechanical advantage. So you can do it with both pieces. But now once you have an ideal mechanical advantage and actual mechanical advantage, in fact in class in the lab you're going to do actual mechanical advantage on a lever, then you can go ahead and solve for efficiency. And if you remember from this slide, efficiency is actual mechanical advantage divided by ideal mechanical advantage. Okay, so that's pretty much levers in a nutshell. We have static equilibrium equations. This is going to be used throughout the mechanical advantage because if nothing's moving, you can find out your distances and your forces. And then our three levers, we had a first class, a second class, and a third class lever with effort forces and resistance forces. Okay, so we'll see you next time.